Dear Professor, our research is standard in platonic polyhedron.
This is our introduction. In triangle ABC, we want to find a point S such that the sum of the distance of segment SA, segment SB, and segment SC is shortest. So we call point S is romantic point. In a convex polygon with more than two points, we want to add some points S1, S2, etc. such that the sum of the distance of vertices to S1, S2 that we added is shortest. Then we call point S1, S2 is standard point. The dark blue path is standard trace. Purpose: find a standard point on a regular polygon. Second, compare the shortest path from mathematical model and bubble-sum form on the Y model. 3. Find the standard point and the standard tree in platonic polyhedron. This is our research equipment.
Material and method. In our study, we start from the standard tree of convex n-gon and then generalize to the standard tree of platonic polyhedron. Now we are going to introduce the planar graph. And in triangle, there are two cases in triangle. First one is the largest angle is less than 120 degrees. And the second one is the largest angle is smaller than it. And in our research, we only use the first case. And the method is we choose segment AB and segment AC to make equilateral triangles. Then connect segment QC and segment BS, which intersects at point P. And point P is the supremate point of triangle. Then the standard point of square. We choose a parallel edge of square, then make equilateral triangles and circumcircles. And connect segment EF, which intersects at S1 and S2. So they are the standard points of square. And in the other hand, we choose point G as the gravity of square. Then consider triangle GAD and triangle GBC. And we find the supremate point of these two triangles, which are the standard points of the square. In rectangle, we choose the shoulder sides to make equilateral triangle and circumcircles. And S1 and S2 are the standard points of rectangle.
Now we're talking about a platonic polyhedron. This is our topic. Next we'll introduce the standard tree of tetrahedron. There is 4 faces, 4 vertices, and 6 edges in tetrahedron. By a former experience we used in school, we consider about triangle GAB and the triangle GCD. We find the standard point is S1 and S2. Then the red path is standard trace of tetrahedron. Next we'll check the bubble form film on the model. We made a copper wire model with each side is 10 cm and another one is 20 cm. We put it into bubble water, pull it upwards vertically and 45 degrees repeatedly. There are only one knot inside. Since symmetric properties, we know that knot is gravity of tetrahedron. Then we found the distance is more than we have in mathematics. We figure out that the distance is the bubble form is minimum path and the minimum energy structure. In 2010 American Journal of Physics, we want to find something to explain why the bubble form is not the minimum path. We'll explore it later.
Now we are going to introduce the standard tree of hexahedron. And first we make a standard tree of a square, then move it to the center of hexahedron. Then we consider these four rectangles. We find the standard tree and the standard point of these four rectangles and rotate it with an angle. Then we found when the four rotated angles are equal 15 degrees. Then the blue edge will match the pink edge. So there are 6 standard points of a hexahedron, and the red edges are the standard trees. And in double solid experiment, we found there are only 4 knots in the hexahedron. By calculus, we can find the minimum path, which is larger than the result we found in mathematics.
Next, we will introduce the spinal tree of octahedron. There are 8 faces, 6 vertices, and 12 edges in octahedron. The 12 edges happen to be the edge of 3 squares. Each square has 2 spinal points. So we have 6 spinal points These 6 spinal points just be vertices of a hexagon after calculation. By inner product, we know that points connect the adjacent the vertices of octahedron is 120 degrees, and this graph is exactly the bubble sort form of octahedron. But by our former experience, it should be 2 spinal points in an octahedron. So we want to remove the two of them and the no cycle in a tree. So we remove the paths connected repeatedly, the vertices of octahedron, and connect the tree. Now we'll remove finally we remove the 2 points, which is the symmetrical to the contour of octahedron, and connect the tree. Finally, now we have standard tree of octahedron, which has 4 standard points and 9 edges. Then we make a mathematical model and find a shorter path than we had. Then we prove it in calculus. The simulation result match the proof. We show the proof on the test.
Now we are going to introduce the standard tree of dodecahedron. There are 12 faces and 20 vertices of an dodecahedron. And we have 2 methods. Method 1, we consider a hexahedron, and there are 6 standard points of a hexahedron. Then we connect the tree. And we divide the dodecahedron to 6 same parts and a hexahedron. Then we connect the red edges. And this is the standard tree of method 1. And method 2, we consider the 3 golden rectangles. And there are two standard points of each rectangle. So there are 6 standard points, which form an octahedron. And an octahedron has 4 standard points. So there are 10 standard points. But in our former experience, we found there are 20 vertices of dodecahedron, so it should have 18 standard points. So we choose the middle point of the red edges. So there are 18 standard points of a dodecahedron. And this is the standard tree.
Next, we'll introduce the spinal tree of hexahedron. There are 20 faces, 12 vertices, and 30 edges in an hexahedron. The 12 edges is exactly the vertices of and three golden rectangles. Each rectangle like is red path and red wires and blue wires and yellow wires. These 12 vertices is exactly the vertices of each rectangle has 2 spinal points. So we have 6 spinal points now, which is the vertices of an octahedron. By former experience, we know that there are 4 spinal points in an octahedron. So we have 10 spinal points of an hexahedron. In the same way, we use algebra to make simulation and find the result match our proof.
Result in discussion. We show our result on this table, and we found if the number of vertices minus 2 is the number of center points, and if V is the number of vertices, and if S is the numbers of center points, and if S equal V minus 2 holds, and we find the minimum path of symmetry. And compared to previous results, tetrahedron and hexahedron are known, and we verify the results. And in octahedron and dodecahedron, the previous results are error, and we revise the result. And we propose the symmetry of hexahedron. In conclusion, we use mathematical software to find the symmetry of Platonic polyhedron. And we finally prove it from symmetry of planar convex angle to 3 dimensions. And if in 2 dimensions, the numbers of vertices of a regular polygon is V, and the number of center points is S, then we have a rule S equals V minus 2. And in 3 dimensions, the number of vertices of a Platonic polyhedron is V. And if the number of center points is S, and suppose S equals V minus 2 also holds, then we prove the minimum path of symmetries. And in our future prospects, we know the structure of adenovirus is an hexahedron, and the structure of symmetry has the minimal energy. So if we destroy the structure of hexahedron, then maybe we can kill the virus. And there are many airports use the structure of polyhedron. So how can we spend less money and have the stable structure? Maybe we can consider our research of symmetries. And this is our reference. Thanks for listening.